Okay, lesson number 4. We're going to solve logarithmic equations. Introduction says there are many techniques for solving logarithmic equations. Much of the work will involve using the laws of logs so that we arrive at one of two possible solutions shown. So they're just showing you right here that if the bases are the same, the log base b of p is equal to log base b of q, in which case, because both sides of the equations are equal and balanced, then p must equal q. Similarly, you could do this kind of an option. If you know that log base b of p is q, then in this case, b, which is the base, to the exponent equals the other stuff, or the argument. So b to the q equals p. All right, so here we go. Alice is solving the equation log base 5x plus 1, equals to 1. Part of her solution, including explanation, is shown below. Here's what she did. She took two logs that were being added and created one log with the argument multiplied together. Then she changed to from logarithmic form to exponential form and said 5 to the 1 is equal to that stuff. You see it there. So now she's going to complete that. So she's going to go like this. Do the math. Bring the 5 over. And you got it. Here goes factoring. You remember how to do that? So that is not the answer. That's the factoring. From that, we can arrive that x is either going to equal 4 or negative 2. It says, explain what happens when you try to verify the values of x in the original equation. So if I was to put that back in the original equation, I would get this. Just copy. I'm going to put a 4 plus 1. Everywhere there's an x, I'm putting 4. Log base 5 of 5 is 1, and log base 5 of 1 is 0. And so we get 1 equals 1. That's all fine and dandy. But what if we plug the other value, negative 2, in? Keep going. Oh my goodness, we have a problem. This is not possible. Why? Because you cannot take the log of a negative argument. So we can't. So negative 2 does not work. My only answer is x equals 4. So in solving this equation, Alice arrived at one of the two positions in the introduction, shown in the introduction. The position Alice arrived at is what? Here's what she did. All right. So here's the note. When attempting to verify the solution x equals negative 2 in the previous example, we reached the situation of a logarithm of a negative number. This is called an extraneous root, or an extraneous solution. In this case, you cannot take the log of a negative number. So a logarithm expression is defined only for positive values of the argument. When we solve a logarithmic equation, it is essential to verify that the solutions do not result in the logarithm of a negative number. You must check to be sure which solutions you're going to choose. Solutions that would result in the logarithm of a negative number are called extraneous and are not valid solutions. Values obtained by solving logarithmic equations may be extraneous and must be verified. When the two verifications required there are two verifications required when the solution is replaced in the original equation. Please go back into the original. There's two things to watch for. Number one, all the arguments must be positive, and the base, if a variable, must be positive too as well. Okay, so you have to check for the arguments and the bases. All right, example number one says solve them. So there's a couple things to do here. If you change this to exponential form, well, in this case, you have the log of both things. Logs are both in base 10, which means x squared has to be 16, which means x could be plus or minus 4. If you were to check that and throw your 4 back in, it would work, because you would have 4 squared. Yep. And the other one would be log of negative 4, but you're going to square the whole thing, and that will work. So you'll get that x can be plus or minus 4. That's a good solution. But let's do it on the right-hand side. What do we do? Well, we can go, oh, let's kick that up there. You're like, isn't this exactly the same? Yes.
Top P extension 0, please, then top P extension 0.
You will get to the same place. However, if you were to check in the original equation, you're going to have a problem. Plugging in positive 4 will be fine. You're going to have 2 log 4 equaling log 16, and those will work. But when you plug it into this, when you plug in your negative 4, all of a sudden, this is not possible. Okay, so watch out for those things. The only solution to this equation here is my positive 4. Okay. Now, if we're to do it using a graphing technique, I don't know if your book has that or not. You could put one into the other. If I type in log of x squared and graph it, I get this funny looking shape that looks like this. And if I also type in log of 16, whoops, I'm going to get this. I'm going to get these two solutions right here. But if I type in this side, if I type in 2 log of x and log of 16, I'm going to arrive at two different pictures. I'm going to arrive at this picture. And this picture, and there's only one solution, and it's positive. Got to get it good? Okay, so why are the solutions, explain why the solutions to the logarithmic equations are not the same, even though one can be written like the other. And that is about domain. Okay, so the domain for 2 log x is x has to be greater than 0. But the domain for log of x squared is all real numbers. All right, turn the page. Here we go. It says solve for x. All right, so here comes our laws of logs. I can't drop my log 4s off yet from both sides until I actually combine these two together. But 2 logs being subtracted can become 1 log with the stuff divided. And now, because we have log 4 on both sides and we have this equality, we are going to put down, we can drop the logs. In essence, because they're equal, then the arguments have to be the same. And you can just cross multiply and divide here. Put your x's on one side, numbers on the other. You get 5/3 when you go ahead and divide by 15. All right. Are we allowed to have 5/3? We better verify. Two times 5/3 is 10/3 minus 9/3, which is 3, which would be 1/3. And when you do the math over there, you get this. All of a sudden, this becomes log base 4, and you have 8/3 being divided by 1/3, which is the same as log base 4 of 8. You go, oh, this is my left-hand side, which is going to equal the right-hand side. So you're done. So your verification worked. That's the right answer. Make sense? All right. What about part B? What are we going to do here? Well, the best thing to do would be to put the logs together on one side and then combine them to make them simpler. So I'm going to go like this. I'm going to add my log 6 from the right-hand side and put it on the left here and leave it equal to 1. So I'm simply going to add that to both sides and move it over. And when I do that, then I have 2 logs being added become 1 log with the stuff or your arguments multiplied together. All of a sudden that becomes, oh, I don't have a log on both sides, but I could say base to the exponent equals the argument. So I could do this. Here's my base, here's my exponent. So that's not so bad. So let's do the math on the left. That's equal to 6. Subtract your 6. And all of a sudden we have a factoring situation. Aren't you glad you know how to factor? So x is going to be -6, or x is going to be equal to -1. All right, are both of those going to work? Could throw them back up and you can see right away that there are some that aren't going to work. So without even checking, if I put a -6 back into the first one, I'm going to have, well, either side, I'm going to have a negative argument. So -6 is not allowed. Does your -1 work? So don't throw it out only because it's negative. Plug it back into these 2 parentheses up at the top where there's a logarithm, and they actually do work. -1 plus 4 gives you an argument with 3. So you are allowed to do that. And same thing with -1 plus 3 in this argument. Don't throw it out because it's negative. Only throw it out if it creates a negative argument. But in this case, the argument will be a 2, a positive 2. So this is your answer. All right, you can press pause on if you need to go back and look at it. Let's do the next question. It says solve 2 log base 3. Oh my goodness, right? What are we going to do? Well, what should we do with the 2 out in front? It's kind of in the way. We can kick it up here. So I'm just going to write a little 2 up there, and I'm going to get rid of that so I don't have to take another step. And now I have 2 logs being subtracted. Okay, that's not too bad. They can become 1 log with the stuff divided. I'm going to take this 3 and I'm going to move it to the other side. So I'm going to add it to both sides and make it a 3 on the right. There. Now I have a log of stuff being equal to 3. And now I can go base to the exponent equals the other stuff. So here I go. Here's my base. Here's my exponent. Cross multiply. That's actually a 27, right? And 27 times 3 is 81. I'm making this a 27, and I'm multiplying across with that. Okay, so now I have x squared minus 27x minus 81. That looks vaguely familiar. I've seen that before. Let's factor. And you're going, factors of 81. The only ones I know are 9 and 9 and 3 and 27, and they will in no way give you a 27 no matter how you do that. So do you know what you do now, class? What do you do when you can't factor something that's a quadratic? We have a formula. It looks like this. You thought you wouldn't have to use this again, huh? All right, let's plug in. B is negative 27, so when I take the negative of B, I'm going to put in the positive 27. All right, when I get all done punching that in my calculator, I should get two different answers. One will be 29.72, and the other one will be negative 2.72. One will happen when I add that nasty radical, and one will be when I subtract it. Now, are they both right? Well, you have to plug those back into the original, so I'm going to erase my ugly messes over here. And if I was to put in 29.72 everywhere there saw an x, I would have positive arguments, which is a good thing. If I was to put in negative 2.72, I would not, because there in the very first logarithm, it would not work. So this one is not going to work. This is going to be my answer. Good. Okay. Moving on. Okay, this is a log of a log. We saw these a while ago in last chapter when we were doing this, and I said work from the outside in. Because logarithms are inverses of each other, it's a good sound, isn't it? Because logarithms are inverses of exponents, we need to work backwards. So normally I would tell you to work from the inside out, but because logarithms are just kind of the inverse, we're going to go the opposite way, outside in. So first step, here we go. Base to the exponent equals the other stuff. And it doesn't matter if all this other stuff is huge and ugly. It doesn't matter. Take your base to the exponent equals the argument, the whole argument. All right, now what do you know? Well, I can do it again. Base to the exponent equals the argument. In this case, my x is a base. Base to the exponent, which is a 2, equals the other argument. Oh, this looks all vaguely familiar. Go ahead, get factoring. This one does factor, which is nice. Do I need to verify which one will work? Well, let me go back up into the original. Always verify in the original. A -1, I see right away it won't work. Not because of the argument, but because of this base right there. I cannot use -1, so I can cross it off right away. Will 4 work everywhere? Yes, it will. Okay. Turn the page. We are almost done. Okay, solve and verify. Solve the equation, log that, using the laws of logs. Okay, so we want to try to get them to be logs, just plain old logs, because then I can combine them together. So this little 3 here, going to kick up here. And then 2 logs being subtracted become 1 log with the arguments divided. And then we can say this is really log, oh, shucks, sorry. We can say this is the log of 1 over x. which is the same thing as log of x to the negative 1. And then you can bring the negative 1 down front. And divide out by it. And then you can say base to the exponent. Oh, wait a second. Where's the base? Well, you can't see it, so it's 10. 10 to the negative 10 equals x. And that's your answer. Another way could be to write 1 over 10 to the 10. Is there an easier way of doing that question I just did? Yes. Let me show you a quick way, just in case. I could have taken and gone the other way and brought this 2 down front. And now 2 log x's take away 3 log x's. Log x's are the same. I have 2, I lose 3, which leaves me owing 1. So boom, right away you arrive at that same place. So in 2 steps, I arrive right here. So I just wanted to show you both ways in case you think to go the other way. It works perfectly fine, but it is shorter to do what I did in the red. Okay, now part B says, explain why the equation log of x all squared minus 3 log x equals 10 cannot be solved. There is a difference between, and I think you saw this on your test, between this, that is not the same as log x squared. Okay, it can't. There's no rule for it on the right-hand side. That actually means log x times log x. We don't have a rule for multiplication of logarithms. We only have a rule for addition of logarithms. So that's why. Part C. Solve the equation in B using the following steps. Oh, they're going to say, okay, let's replace log A by a new variable A. So they want you to say, this is really A squared minus 3A equals 10. They want you to replace everywhere you see a log x, put an A instead. Now let's solve for that. So we're going to factor. Um, 10, 5, and 2. Oh, the 5 and have the 2. So A equals 5 or A equals negative 2. Now we're going to go back and put log x back in. So log of x equals 5 or log of x equals negative 2. All right. So in which case I can switch from logarithm to exponential. These are base 10s. You could put a little 10 here if you wanted to. Don't forget that. So I have 10 to the 5 equals x or 10 to the negative 2 equals x. And you could check those and they would work. You're all good. There's your answers. So it's 10 to the 5 is the same as that number. And this is 1 over 100 if you want. All right, so there is a way to solve part B, but there's no laws of logarithms. There's no rule about logarithms to solve it. You have to put it into quadratics and solve it that way. All right, here we go. Part D. A student is solving the logarithmic equation log of x squared minus log of x cubed. Her work is shown. So she's like, oh, I'm going to do the same thing. I'm going to put A as log x. That's what we just learned, right? So she puts it in here. She turns this into A squared, all well, and she puts it into here. There's a problem. What's wrong with that? This is not, she assumed that this was what she was doing. That would be true, but it is not. That is not what she did not do the right process. Okay, so this was the error right there. Here's what she should have done. You can leave this as A squared if you want to, but this should be 3 log x. Bring the 3 down in front, and now you can replace log x with A. That is what she should have done. See the difference? And now you can factor out an a if you want to. So now either a equals 0 or a equals 3, in which case now we'll go back and replace a with log x. And x, in this case, this is a 10 down here if you want. So we have base to the exponent equals x, so x equals 1, which you already knew. And this one is 10 to the 3 equals x, in which case x is 1,000. 2 answers. Any problems with those answers? Can I put them both in? Sure, you can. You could go check them. They would work. All right. Good luck.